Thanks, Miles. OK, so yeah, my name is Ankur. I'm a grad student in the AMP lab. I also worked on GraphX previously. So today I'll be talking about a new project for supporting graph queries in Spark. And this project was a natural extension of GraphX in two ways. One is that we kind of wanted to rewrite GraphX to support data frames as the whole Spark project evolves from RDDs to data frames. And secondly, we wanted to continue, from the research side, continue GraphX's idea of unification by integrating graph algorithms and graph queries in some deep way and optimizing across them. So this talk will actually be about the research, focusing on the research behind GraphFrames. And then Michael Malak's talk next will be more about actually using it. So you can stick around for that if you're interested. So let me start by looking back at the history of graph analysis in Spark. So Spark started with, of course, the RDD model, which you can think of as like relational or data parallel transformations. And the insight of GraphX was that you can express graph algorithms using these relational operators, plus some optimizations underneath to make it fast. And then in GraphFrames, the idea here is that we can do the same thing, but for graph queries as well. Now, here, when I'm talking about graph queries, it means something similar to in graph databases like Neo4j. There's a subtle distinction, which is that we're talking about batch queries that touch the whole graph, while databases like Neo4j provide a separate feature set where they support efficient transactional updates and traversals from a small set of starting points. And I'll touch more about on this distinction at the end. But OK, so first of all, what are graph algorithms? What are graph queries? What's the difference? So graph algorithms are things like PageRank and alternating least squares, ALS. These are algorithms that are expressed usually as a sequence of steps where vertices pass messages along edges. On the other hand, graph queries are given a small pattern, find all occurrences of it in the graph. So it's also known as subgraph isomorphism. And of course, as the pattern grows, this actually becomes really hard quickly. But even limited to relatively small patterns, maybe like 10 vertices, this can be a very useful tool. OK, now here's an example of each, algorithms and queries. So PageRank is a really popular graph algorithm, and it operates on a graph where the vertices are web pages and the edges are links between them. And this PageRank algorithm calculates how important each page is if each link is a vote of importance, and then if votes also count for more if they're themselves coming from an important page. So let me replay this animation, and you can see that these votes are being passed, and then according to who gets which page gets the most votes, these ranks are being shifted accordingly. OK, on the other hand, here's an example of a graph query in a Wikipedia data set where vertices are users and pages, and edges are edits. So that as an edge represents a user editing a page at a certain time. So since I've mentioned this time on each edge, that means each edge needs to have an associated property, which is in this case the time. And that makes this kind of a graph called a property graph. Anyway, so this query with the 4 vertices there finds users who collaborate often, sort of pairs of users who collaborate often, which I'm just defining as when they edit the same page within the same day. That's how I've defined collaboration here. And so the idea is that if 2 users are collaborating on 2 different articles, then we want to maybe get their usernames and get the articles they collaborated on. And then this graph query would return that information as a table with 1 row per match. Now, here's an example of what each of these looks like in code. First, here's how to express the PageRank message passing algorithm in GraphX. You can see that you sort of pass a vertex program that runs on each vertex and that has a closure, and also one that merges messages and applies the message sums to the incoming to the destination vertex. And then here is that same Wikipedia query in the system GraphFrames. And notice that it's sort of, first of all, has a declarative API where you can express the structure just using sort of this ASCII art-looking query. And also, there's this integration with data frames. These are all just data frame operations that you can use to apply those date filters. OK, so now first of all, why introduce this new library, GraphFrames? Well, currently we need separate systems to support each of these tasks, the algorithms and queries. So to run message passing algorithms, there are a bunch of specialized distributed graph processing systems that can only do graph algorithms that generally can't do relational operations or graph queries GraphX, of course, aims to integrate the relational operations with the graph algorithms, but still can't do graph queries. So there's kind of no system that does all of them. And then on the other hand, to run graph queries, there are a few graph databases that accept queries in a few standard formats. So there's a Cypher and Gremlin are popular ones. And now most of these graph databases actually do support running relational operations on the results, but they're pretty inefficient if you wanted to run a whole graph algorithm, something like PageRank, hard to express and slow in these. Okay, but real graph analysis often involves doing both. So if you wanted to, just going back to Wikipedia, if you wanted to do some analysis on that, then here's kind of an example of what that might look like. You might take the raw data set in XML as the dumps come out, parse it and extract it into a table with these articles and links between them, and then you can turn that into a graph. But you also might want to take the same base data, parse it differently, so maybe take out the edits instead of the article text. So then there it's a user editing an article, and then again that forms a different kind of graph, a bipartite graph. And now here you can run a graph query. You can do something like that same query that I mentioned earlier, like which users are collaborating frequently, and you can see it requires information from both of these different graph views. But there are other queries you might want to run. So one of the queries that I came up with is you might want to find users who are making like low quality or vandalism edits. So low quality edit, you can kind of figure that out by saying, okay, if a user edits an article and then shortly afterwards some other user reverts it, then that's probably might be vandalism. And also you might want to normalize by the overall kind of importance of the article, because maybe more important articles get vandalized more, something like that. So PageRank will let you do that. And that's a graph algorithm that you have to run to get that information. And then you can run a graph query to figure out vandalism. So that's kind of a made-up example, but it captures the general idea that you often need to do 3 different operations on the same base data. You need to do relational operations, that's the parsing and other table transformations. You need to do graph algorithms, things like PageRank, and you need to do graph queries. Okay, so the solution of GraphFrames is one that combines pattern matching, it's graph queries, and graph algorithms, and relational operations in a single system, and also tries to optimize across them, which is kind of where the research comes in. And then this is built on Apache Spark SQL, and it's available as a Spark package, and I'll give a link at the end. Okay, so the API, here's just a quick look at what the API looks like. So it exposes, well, first of all, the idea is to do this unification. And also, the nice thing that might be really interesting for just real-world use is that it's available in all 3 of the major languages that Spark supports. Whereas GraphX, you may know, was only supported in Scala, and yeah, so that's a big thing for the real-world use. But anyway, here's what the API looks like. So first of all, you can given a graph, a graph frame, you can get back, of course, simple views of the graph as data frames. Then the key thing is there's a way to run a graph query and get the table of results back. And then there's also a way to hint to the system that certain patterns are going to be used a lot, so that we're calling those views that you can register. And there's a library of common graph algorithms, same as in GraphX, and also a way to write your own, not shown here. Okay, now here's an overview of how this actually works. So given a graph query string, right, how do we take this and get the results? Well, first of all, we have to parse this query string, which looks like the one I showed a few slides ago. And we actually use Scala parser combinators to do this, which makes it very concise, so that's nice. And then we need to translate this kind of a pattern query into a relational plan, which is something that we can eventually give to Spark SQL to execute. So a relational plan is just a sequence of joins and other relational operators and so I'll talk about how this translation happens. And then next, if the user registered views, those common subpatterns, then we want to look through those and insert them into the plan when possible. And we also want to apply there's certain custom optimizations, graph-specific optimizations, that we can apply to this plan. And then finally, we can pass it into Spark SQL, which will finish optimizing and run it. Also, there's this sort of current separate code path, which is that for legacy graph algorithms that were written in GraphX, there of course is the main option of rewriting them in GraphFrames. But for the more complicated ones, we can still actually call out to GraphX and then reuse those algorithms. Okay, so next I'll go into detail on 3 of those stages that I've labeled here. So first of all, I want to give a sense of how these graph queries translate into relational operators. So let's consider this little simple pattern query. We've maybe already matched A, B, and C. So that is, we're going to imagine that we are a stage in the Graph-Relational Translation, and we already have the partial result sort of from that gives the ABC triangle. And now we just want to finish this pattern match by joining in the CD edge. So okay, so to do that, we do just that. We join in the edge table with this constraint that the common vertex C has to be constrained to be equal to the source ID of the vertex. Sorry, of the edge table. And then also we've introduced this new vertex D. So to get the vertex properties of D, we have to join in this vertex table. And again, there's the same constraint. This is a pretty straightforward way of just taking a graph pattern, and then for every edge and every vertex, we just generate a join to bring in to repeatedly bring in like each of the vertices and edges in that pattern. So we're sort of just generating a lot of joins. There's going to be a ton of joins from this, and then the kind of overall strategy is that we can do that, and then let them be removed by a later stage of the pipeline, depending on whether or not they are actually necessary. So if for example, you don't really need the vertex attribute for C, and it's only there for sort of the structural purpose, then there's this later step called join elimination, where the join for C will be removed. Okay, so the next thing I'll talk about is the stage of the view selection, where we have a set of registered views that the user has given us, and those are the common subpatterns, and we want to figure out whether or not where to insert them into the plan. So actually, it's a little bit complicated, the algorithm, so I won't go into detail on how it really works, but I'll instead just motivate it by saying that, so first of all, one of the insights from the GraphX research was that there is this triplet view, which corresponds to joining the vertices and edges so that each edge gets the vertex attribute from its source and from its destination. And I'm missing a vertex here, but you can see, like, if you look at the AC edge, then you'll see that it has the vertex properties as well as the edge property. So one of the insights from GraphX was that materializing and maintaining this triplet view gives rise to a lot of the optimizations that the GraphX used to get good performance. And also partitioning the view was a big deal. So from this insight there's a special view in graph processing called the triplet view. In GraphFrames, we're kind of aiming to generalize that idea and say that not only can you register this triplet view, but also you can register any user-defined view, and it should be maintained and used in the same way that the GraphX did just for the triplet view. So it's kind of this nice generalization of the concept of views from GraphX to GraphFrames. So there's the motivation for having views. The next thing I want to, the last sort of piece I'll talk about is this join elimination. Actually, second to last is this join elimination stage that I mentioned earlier. So let's just consider a small example of a vertex and edge table. There's an important property that the vertex and edge table satisfy, which is that first of all, the vertices are unique on their vertex ID, and the edge table. The source and destination vertices are foreign keys into the vertex table, meaning that every source and destination ID has to correspond to some actual vertex in the table. So the combination of these two constraints means that when we join the vertices and edges together, then the join satisfies what's called referential integrity, and that property means that we can apply this optimization. So consider this join where we're joining the vertices with the edges. On say the source, so that is we're bringing in the source vertex property, and then suppose we're only just selecting out the source and destination vertex IDs. So in this case, it might be clear if you just work this out by hand that this is just equivalent to just taking the edge table. So it was not necessary to join the vertex table in at all, and that's true only if these tables do satisfy this constraint. So what we've done is that we've added some optimizer rules and these key hints into Catalyst, the unique and foreign key hints. And then with that, Catalyst is able to automatically do this this join elimination, and then that really simplifies the graph-relational translation because it can rely on Catalyst having this special knowledge about these vertex and edge tables. Okay, now the final thing I'll talk about in this sort of the dive into the internals is this stage of join reordering, and this is a key part of making graph queries fast. So let's just consider this example query that has these 5 vertices now. It's a little more complicated, and it has a whole bunch of edges in between them. If you just feed this query in to a standard database like Postgres or even to Spark SQL, it'll likely result in the plan that looks something like this, which is it'll be a left deep plan, meaning that we only have one intermediate result into which we just keep joining in each next edge and vertex property over and over. And this is also the same thing that will come out of the graph-relational translation, just using that simple scheme. So that's OK, but it turns out that there's actually a much better bushy plan, so-called, that builds up 2 intermediate results and then joins them together at the end. So you can see here that there's one intermediate result from this join, and there's another more complicated intermediate result, and then just by joining those 2, we get the result. Now, OK, so what's so great about the bushy plan? Well, the answer is, first of all, the intermediate results, turns out, can be much smaller in this case. And the other thing is, if you count the number of joins, there's actually one fewer join in this bushy plan compared to the left deep plan. And that's actually a huge deal because these joins, they're each very expensive. So OK, why can we do this? Well, it turns out that this query has this interesting property that there are actually 2 subqueries of it that are identical. So if you take a look at BCD, you'll see it's this triangle-looking thing. And then BCE actually is also the same triangle structure if you just convert D to E. So BCD and BCE are isomorphic. So finding that insight and finding this bushy plan query automatically is actually very difficult because there's a huge search space given even this relatively small number of joins, since it's like super exponential. But if the user helps out by just doing one simple thing, which is to define a view, registering a view on BCD, then our planner can actually find this. And for a real query, if we're doing this, then the BCD probably has some real domain-specific meaning that the user knows about because it's being used twice here. And so the user can improve performance just by passing that knowledge on to the system. And for example, kind of our thinking is that in interactive session, you might define some views, and then you might refine them in some exploratory way, and that will lend itself nicely to this kind of optimization. OK, so now finally, we have a few preliminary experiments that try to show the promise of GraphFrames. So the first thing we did was we compared against Neo4j, which is a graph database that also supports graph pattern queries and actually happens to support them in a superset of the query language that we use, which is Cypher. So we ran, first of all, 2 versions of sort of the same query. The 2 versions are what we call anchored and unanchored. So an example of an anchored query is something like, so suppose we just take a social graph, like how many of my friends know each other, right? So that's a triangle query where there's me and there's 2 of my friends, and they should know each other. But it's anchored because there's this unique constraint that the vertex that represents me can only have one match in the graph. There's only one user for me. On the other hand, an unanchored query is just, in general, in the whole graph, for every person, how many friends do they have that know each other? And that's the so-called famous triangle query that is a common benchmark in graph systems. But that one's unanchored and therefore is much harder. It has many more matches. So here are the results for each of these. The anchored query, we're a little bit slower than Neo4j, which is not surprising because they're really optimized for these kinds of anchored queries. They have specialized indexes and a specialized traversal scheme. But that's expected. But for this unanchored, more analytical query, we're actually a lot faster than Neo4j, and this is the kind of query that we are targeting and are trying to optimize. OK, second, we wanted to compare against the system that we're eventually hoping to replace, which is GraphX. So we compared against it on an iterative graph algorithm, that's PageRank. And so it's kind of, even though GraphX has a lot of optimizations for PageRank that we actually haven't yet implemented, It turns out that we're actually quite competitive with it, which is a little surprising. So we're almost as fast as GraphX there, and this is kind of the just for comparison, it's how slow it would be to implement the same thing in just using RDDs. There's actually a Spark example that does this. Okay, so now why is it why is there this surprising result that we're so fast? Well, it's because mostly because we benefit from the speed of Spark SQL in Spark 2.0, which does whole stage code generation and uses off-heap memory and has a bunch of nice execution optimizations that GraphX couldn't have used, but that we're able to take advantage of. So even without having all of the work put into the query planner, we're able to still do this. Okay, now finally, this is the final evaluation slide. So we wanted to run an existing sort of a graph query workload and figure out whether this view registration thing really, how much it helps in practice. So we took a kind of fairly standard set of 6 graph queries, and this just comes from some graph database literature. And then we wanted to run. then we materialized these 4 views, which sort of felt natural. And seem to show up a lot. So things like a 2-cycle or a triangle are the kinds of views. And then we ran these 6 queries using GraphFrames, but with and without registering those same views. So these columns here are the lighter colored columns are the ones without using views at all, and then the right side columns are the ones with views. So you can actually see that mostly registering views doesn't really help that much for a lot of these simpler queries. But there are a couple of queries that are interesting, which are queries 4 and 5. So query 4 is that one that I was showing earlier, where we have this special plan that we can discover by registering a view. And there you can see that indeed, if you do that, you get an almost 10x speed up, even including the time to actually register the view first and then run the query. So that's cool. Then the other thing is query 5, which you can see that the total time is pretty similar, 30 and 34 seconds for each of these. But on the right side, you can see that creating the view actually took most of the time, and then thereafter running the query was pretty fast. So we think that's interesting because we were able to front load a lot of the work into just the view materialization, and then we can quickly run the query. And that makes sense for sort of an interactive session where you have some views that are maybe expensive to compute, but then you want to run some kind of queries afterwards, and you want those to be as fast as possible, given that you've already put in this pre-processing time. So this is kind of a promising result for the idea of views. Okay, so I'm almost done. There's a few things that we're interested in on working next. There's some things in research, so we can sort of suggest views automatically. We want to exploit the fact that there are actually attributes and even partitioned attributes for making the optimizer faster. We also want to make sure that we can scale down as well as scaling up. So of course it's easy to scale. I mean, but it's a popular goal to be able to scale out to hundreds of nodes. But what about making a query really fast on one node? There's some interesting ideas in code generation and others to make that fast. And also, we would like to have better integration with systems like Neo4j, so that hopefully, ideally, you can just sort of write one query and then choose which system to run it in, and then have compatibility at the language layer. Okay, so that's with that. I just want to say that we have a Spark package release. It's available for Spark 1.4 Plus. Now, some of the optimizations that I talked about are still in the research phase, so they aren't actually in the release yet. But it's very usable, and it's still pretty fast. And thanks to the people from Databricks who have done a lot of work on making this very well documented and usable. And with that, that's all I have. Thanks a lot.
Awesome. Thank you very much, Ankur. Any questions?
Maybe this is naive, but why a DSL for find?
Say that again?
Find uses a DSL. Why?
Oh, so why use a DSL rather than try to have some sort of language integrated query? So the idea was that we saw that there's this existing kind of nice way of expressing pattern queries, which is Cypher, and we wanted to just sort of reuse something that might be familiar for people. But that's true. It could have been. It could be that in the future we might want to have something that's more like data framey and more language integrated. We haven't thought too much about that.
What's in the way of completely replacing GraphX with GraphFrames?
So what remains for replacing GraphX with GraphFrames? Well, first of all, there's still some performance, kind of a performance disparity because of there's a lot of work that went into GraphX, and we haven't yet done that all for GraphFrames. So we don't want to make people think slow down just yet. And also there's some annoyances with having exact API matching, and so we would ideally prefer to have source compatibility, and we aren't yet there, but eventually we expect that to happen.
Great presentation, thank you. So when I was using GraphX, primarily the difficulty has been every time I load the graph, it is just one graph. And if I want to add new edges or new vertices, it's just another batch job. So is GraphFrame one step toward allowing us to do updatable graph databases type of thing?
Yeah. So about updating graphs, we haven't really attempted to solve that problem with GraphFrames. So it'll still be something similar, although since there are kind of fewer index structures that we're building at the moment, it actually will probably be faster to add a vertex or edge, because rather than rebuilding this whole graph, you can just add them to the data frame and then rerun the query. But there is some ongoing research. Actually, yesterday I gave a talk in place of Anand, who is working on trying to make this efficient using some special data structures underneath. So that's probably the best answer. And one other thing is that in practice currently, if you wanted to do this, one way might be to use to make the updates into a database like Neo4j, which does support updates efficiently, and then periodically just pull import from Neo4j into GraphFrames. And in fact, there's actually a connector now that's out from Neo4j.
Any more questions?
So is there any way we can contribute to GraphFrames?
Oh, contribution, yeah, absolutely. This repo, though it's not like officially under the Apache code process or anything, they welcome pull requests, and these maintainers will do a good job. Eventually, we would like to get GraphFrames merged into Spark, and then you can just go through the Apache process, of course.
Any last questions? All right. Well, thank you for coming, and let's give Ankur one last round of applause.
Thank you.